we shall now start chapter 5, which is mass and energy analysis of control volumes. So now it's the chapter 4 was about the energy analysis of closed systems, but here this chapter is about energy analysis of control volumes. So control volume simply means the open system in which mass is entering and mass is also leaving. That's why it is not just energy analysis. You can see here the term mass is also written, because now we are discussing about the control volume. So it is not just energy analysis, it is mass and energy analysis of control volumes, because mass is not fixed within the system boundary. Mass may enter and may leave the system boundary, the thermodynamic system boundary. So this chapter is also mainly covered from the 8th edition of Yunus and Sengel, and at some places we have taken some reference material from these other books also. Right, so this chapter 5 is again the extension of chapter 2, the first law of thermodynamics. So here we shall again be applying the first law of thermodynamics, but not to a closed system but to control volumes. So that is all the numerical problems which we shall solve in this chapter is actually related to the control volumes, in which continuously there is a fluid which is flowing across the system boundaries. So let's start. So here we have already discussed something about this control volume in chapter 1 and 2. So here you can see control volume. This is our system across which some mass is entering and some mass is actually leaving that system. And here the example is shown for a steady flow system. So we have already have some idea regarding these steady flow systems, that steady flow system or steady flow devices, because a number of engineering devices which are used in practice are actually steady flow devices. For example, this device could be a turbine in which mass is entering, mass is leaving, and we are getting some work output. So the same control volume could be a compressor, in which again some mass of fluid is entering, the same mass of fluid is leaving, and during this process some work is done onto this control volume if it is a compressor. Similarly, this control volume could be a nozzle where mass is entering, mass is leaving, and from inlet to outlet its velocity is increasing. So this control volume could be a boiler, it could be a condenser. So any such device in which continuously there is a flow of mass which is entering and the same flow of mass which is leaving. There could be more than one inlets, there could be more than one outlets. And we shall be restricting ourselves in this chapter to only steady flow systems. So steady flow systems also means that the amount of mass which is entering and amount of mass which is leaving, it is same. So the mass of that control volume with respect to time is actually a constant. It will not change. So steady flow process have a number of characteristics. One of them is that the total amount of mass flowing through this system is constant, and also the no intensive or extensive properties like temperature, pressure, volume, etc., or enthalpy or internal energy. All such extensive or intensive properties, they do not change with respect to time. They may change with respect to position. So for example, here the fluid is entering at certain temperature T1, pressure P1, volume, specific volume V1. It has certain mass flow rate m dot, right, m dot 1 at inlet. Similarly, now it is leaving at new temperature T2, pressure P2, volume V2, and mass flow rate m2. 2. And some other thermodynamic properties, like for example, at this point its internal energy is given by U1, its enthalpy is given by H1, and entropy, which we will study in in coming chapters, another thermodynamic property. So all these are thermodynamic properties of this fluid, which is entering into this control volume and leaving with another control volume with some different value at exit. So we can say that all these values of thermodynamic properties, their values are changing with respect to position, but with respect to time all these remain constant. So then it is a steady flow process, means all these intensive or extensive properties, they do not change with respect to time. So when and also it means when we are saying that the enthalpy change or kinetic energy change or the potential energy change, this change from inlet to outlet is not changing with respect to time. So in other words, this means that the overall energy of this control volume is also a constant with respect to time. So then it is a steady flow system. And fluid properties at inlet and exit may be the fluid properties at inlet and exit, they can be specified with their average single values. For example, at this point the mass flow rate has certain value, 1 kilogram per second. Temperature has one single value. We can assign one single or averaged value at the inlet. For example, it is 20 degrees Celsius, pressure is 1 bar, specific volume is 0.1 meter cubes per kilogram. So we can assign a single value to this whole mass of the fluid which is entering, and when it is leaving, now this whole mass, the same whole mass, has now some new value of specific volume, temperature, pressure. So this whole mass is the whole mass means at molecular level these values may be different, but at microscopic level this averaged value is almost fixed, and it is not changing with respect to time, but they are changing with respect to position. And also when we are saying the energy of this control volume is not changing with respect to time, erase it. So when we say that energy of this control volume is also not changing with respect to time, so it means whatever energy is being transferred with the surroundings, it could be in the form of heat, if it is for example a boiler or a condenser. So in case of boiler, heat would be in case of condenser, heat would be leaving this control volume. In case of boiler, heat would be entering into this control volume. If it is a turbine, then work is being extracted from this control volume. If it is compressor or a pump, then work is done onto the system. So all these heat and work interactions between this steady flow system and its surroundings, they are also not changing with respect to time. So a constant amount of heat is being transferred from the control volume to the surroundings, or from the surroundings to the control volume. So heat and work interactions with the surroundings, those are also constant if it is a steady flow system. And here we shall be discussing only steady flow systems, because all the systems, most of those thermodynamic systems in practice, those are designed for steady flow processes, like turbine or compressor or nozzles or boilers or condensers or any other type of heat exchangers, heat exchangers. All these devices, in majority of thermodynamic systems, their purpose is to operate steadily for a long period of time, right? So that is written here, steady flow devices. We shall be discussing only steady flow devices in this chapter related to mass and energy analysis of control volume. So which control volumes, which are steady flow devices, right? So I have already explained this thing. And for example, here as an example, it is shown and the example of an air compressor, where air is entering into this control volume, And what is this control volume? This control volume is actually an air compressor. So mass of fluid, it is entering into this control volume, and the same mass is actually leaving, and the work is also entering into this system. Work is also crossing the system boundary. Right. So for steady flow system, we also said that the total amount of mass which enters the system is also equal to the total amount of mass which is leaving. Right. So there is no mass accumulation within the system, which is another one of the thermodynamic property, or one of the characteristics of steady flow system, that the total amount of mass, uh, there could be more than one inlets. So that's why the summation of all the mass flow rates which are entering into a control volume is equal to the sum of all the masses which are leaving the system. And this mass, using one-dimensional approximation, we can, because actually the velocity is not same in this cross section. For example, this has been projected here to show this pipe through which fluid is entering into this control volume, and we know actually the velocity profile would look like this one. Right, velocity near the walls, it is near to 0, and then it is increasing, and highest at the center of this duct. So lowest velocity magnitude is at the ends or at the walls. So velocity distribution, actual velocity distribution is like this, but we assumed it to be a constant or averaged velocity. We assume an averaged velocity over the whole cross section of this duct or pipe or passage. Right. So and we are assuming that the fluid is flowing in one particular direction. It could be x. So the fluid velocity component, or the component of its mass in the y and z directions, are negligible. So it means for this inlet, fluid is only moving in one dimension, and that dimension is the x direction, positive x direction. Similarly, at this end, when it is leaving the control volume, all of the mass is moving in one particular direction, and that direction in this case is positive y direction. Right, so there are the x and z components are negligible. So in this case, I think we have already discussed in previous chapter somewhere that the mass flow rate for one-dimensional assumption, that we can say that this flow which is entering is normal to this system boundary. Air fluid mass flow rate is normal to this boundary, control volume boundary. Similarly, here the fluid mass flow rate is exactly normal to the control volume, and all the intensive properties like temperature, pressure, velocity, etc., or velocity or density, they are uniform with respect to position at the inlet. So their values are taken as the bulk average value at this entrance or at this exit. Bulk average value means this whole mass of fluid has one fixed temperature, volume, pressure, etc. All those intensive properties have one fixed value, or that is called bulk average value of this fluid which is leaving or entering this control volume. And for that case, m dot is given by rho, the density of the fluid, multiplied by cross-sectional area of that passage perpendicular to which this fluid is moving, multiplied by velocity in that particular direction, v. So that is the mass flow rate, and that is called one-dimensional flow form of mass flow rate balance. Right. So from here we can find out m dot using this one-dimensional flow assumption. Or in other words, we can also write it as area into velocity divided by specific volume. So rho is equal to 1 over v. So that is another approximation which is normally used in the study of these steady flow devices or control volumes. Okay, let's move on. Now we shall apply the first law of thermodynamics for a control volume, not a control mass, so it's a control volume under steady flow. So now we know very well what is meant by steady flow, and also we know what is meant by control volume. And we have already studied the first law of thermodynamics, the mathematical forms of first law of thermodynamics for various cases, for control volume, for control mass, and for a cycle also. So for now we shall be studying this first law of thermodynamics only with respect to control volume under steady state operation. So here you see in this diagram that it is some system, some control volume, right, where all the possible energy interactions with the surroundings are shown. For example, here mass is entering into this system. This is not some actual system. It is not any practical system, just schematic to represent that, to represent various types of energies which may be crossing the system boundaries into the system or out of the system in the form of heat, for example, in the form of work. So this is shaft work. Here this is boundary work, moving boundary work, which we have already studied. And here is the energy entering in the form of mass, because now it is a controlled volume, so mass is must be entering into this control volume, and the mass must be leaving out of this control volume too. Right. So when mass is entering into a control volume, it must be entering, it would be entering with a certain pressure, temperature, velocity, and based on this it has certain energy mass when it is entering, because the energy of the mass is not zero, because whatever fluid or whatever fluid in the form of liquid or gas which is entering into this control volume, it already carries some energy with it, which is represented here with small e, right? So fluid which is entering into this control volume, it already carries some energy in it. So what types of energies this mass carries with it? Due to its temperature, it will have energy in the form of internal energy, plus because of its velocity, because it is moving with certain velocity, it has energy in the form of kinetic energy, half v square. Now I am writing everything for a unit mass. Similarly, it may have certain energy in the form of potential energy Gz, right? So the energies like electric input, electric potential or surface tension effects, those are not considered for majority of thermodynamic systems. So then the energy of this mass which is entering into this system consists of mainly these three parts. Now there is one more type of energy which is known as pressure energy. So let me describe this separately, because let me show it this part at which the fluid is entering into this system separately here. So there is the pipe in which this mass of fluid is entering. So let's assume this mass of fluid consisting of number of small elements. For example, this mass of fluid which has entered into this system. Why it is entering? Because it experiences pushing force from the fluid particles coming behind this. So this is a fluid particle which is entering into a control volume. Why? Because it gets some pushing force from the fluid volume which is behind this one. That's why it enters. So it experiences a pushing force from the mass which is behind this fluid volume, finite fluid volume. So that's why it enters into a system. So this pushing force is known as, because of this pushing force which acts on this fluid volume from the fluid particle coming behind this volume, is actually producing work, because there is a force into displacement due to this push and that is known as work, flow work, there is a flow work onto this fluid element, due to which it enters into this control volume. And how it is given, we can write it. It is in the form of F into V, because this push which it gets from the previous, or from the fluid particle right behind this one, this push is actually F, and that produces a velocity which is F into V. So F into V becomes a work done, WFW dot, because this is newtons and this one is meters per second. So Newton meter per second becomes joules per second. And what is this force? This force can be written in terms of pressure and area. For example, this force can be written as P into area, differential area, dA, which can be integrated over this whole cross-sectional area. So P into this whole cross-sectional area over which this force is acting. So F can be replaced as P into dA into velocity. Right. So that is the push work or pushing force which produces this flow work, and that's why this fluid is flowing in that particular direction. So that is an extra energy which a fluid carries when it enters into a system. So that energy is in addition to these three energies which this fluid is carrying with it, right? Now let's see. Now F is replaced with dA into V. So now P into what is this, velocity into area product, that represents volume flow rate. So now this can be written as P into capital V with dot. This is velocity, but this V with dot represents volume flow rate, because volume, velocity into area, now it becomes meter cube per second. So that is the P into V dot product. So which we can write in the form of small v. So this flow work can be written as P into V into M dot. So we can replace V dot, capital V dot, as M dot into small v, where small v is specific volume. That was the total volume flow rate. Now it can be written as M dot into small v. So that is the flow work, or that is the flow energy which is present here, because of which this fluid enters into the system. So whenever this mass flow energy transport occurs, whenever there is a mass crossing the system boundary, it consists of two parts. The first is the total energy associated with this flow stream. This is the total energy, right, with the flow stream or with the mass itself. And the second is this one. What is this one? Second is the energy required to push the flow stream of this mass, flow stream mass, across this system boundary. This part is often known as flow work. This part, PD A into V, or P into V dot, or P V into M dot. This is known as flow work, which is in addition to this one. This is the energy of the fluid which it carries as itself, right? And this is the extra push due to which it enters. The same is present here when it is leaving. So now when it is leaving, it will have a new U, new half V square, new GZ, and new PV M dot product, because now the same push is experienced by this fluid which is leaving the system boundary, because there is a push behind. These are the fluid particles. Why they are flowing in this direction? Because they experience this force from the fluid coming behind them. So the same energy, so you can say this is PI VI MI at the inlet. So similarly at the exit, it is PE VE, the flow work, VE M dot E. Right. So for per unit mass, we can say this flow work is P into small v, right? P1. So we can write it here that the energy of the mass consists of four parts: internal energy, kinetic energy, potential energy, and flow energy or pressure energy. So this is the total amount of energy with fluid which this mass of fluid is carrying with it, and it is entering into this control volume with this total amount of energy. And now the same mass is also leaving, so now it will be leaving with this energy at exit with E, subscript E, because now we are dealing energy analysis of steady flow systems or control volumes under steady flow. So now we have to take care of these energies of the mass also, because in the previous chapter it was a closed system, so the only energy with which the system was interacting with the surroundings, it was either in the form of heat or work. There was no energy of the mass involved, but here the energy of the mass has to be taken into account when we shall be solving such systems where there are energy interactions with the surroundings in the form of heat, work, and also mass. So this explanation which I have given you is also explained in the book and also slides, so you can read them again by yourself. So I have explained each of these terms. So now one more thing here, the energy of the mass. Here we can combine these two energies, internal energy and flow energy, and that becomes enthalpy. So energy of the mass consists of two parts, small e plus flow energy, right? So small e is actually u plus half v square plus gz. So here v is velocity, not volume, right? So here in this bold v is velocity, and this v with dot, which is not bold, that is volume flow rate. So please be careful about the difference between these two v's. One is bold v and this one v with dot, that is volume flow rate and that is velocity. So that is the total amount of energy which fluid carries, and here we can combine these two energies, the flow energy plus internal energy, and that becomes enthalpy. So that is the total amount of energy with which fluid enters and leaves the system. So now we can apply the general energy balance to a steady flow process. So the general energy balance means first law of the equation of first law of thermodynamics for control volumes, and we already know that this is the first law of thermodynamics, the general equation of first law of thermodynamics. Here this E dot in and E dot out represents the rate of energy transfer into or out of the system in the form of heat, work, and mass, because now we cannot neglect mass. And here is the rate of change of energy within the system, dE of system divided by dt. And for a steady flow system, one of the characteristic of steady flow systems is that this change in energy of the system with respect to time is zero. It doesn't mean energy of the system is zero. The system and the change in energy of the system with respect to time, because all the amount of energy which is entering is equal to the amount of energy which is leaving, so that's why this change is zero. So for a steady flow system, we can simply write E dot in is equal to E dot out. But what is E dot in? Here E dot in is the energy in the form of heat, work, and mass. Q dot in plus W dot in plus the energy of the mass. So energy of the mass consists of a number of parts. Here this theta is actually the summation of all the energies of this mass. There could be more than one inlet, so that's why here is the sigma for all inlets. So we have to add the masses and their energies from all the inlets. Similarly, there could be more than one outlet, so summation of all the energies of the mass which are leaving the system. And what is theta? Theta represents the energy of the mass. And for a flowing work, we know energy of this flowing fluid per unit mass. This theta is actually consist of these three parts which we have studied or discussed in the last slide, that this theta is equal to H plus KE plus PE, where H actually consists of two parts, U plus PP. Right, so just write here. So here you can see this form is transformed to this one. So this is the general energy balance equation for a steady flow system, which is a control volume, right? So Q dot in plus W dot in plus sum of all the energies of all the masses which are entering, and the mass and the energy of the mass consist of these three parts, H plus V square by 2 plus Gz. So these are the energies entering the system, and these are the energies which are leaving the system. So this is the general energy balance equation, which we can apply to any steady flow thermodynamic system or thermodynamic device. Right. So here again, let's consider some control volume in which fluid is entering with certain mass mi, fluid is leaving with mass m dot e, that is exit. So this is our boundary or control volume. This control volume is absorbing heat Q dot, and it is doing work W dot. Right, so that is the general form of any control volume. Right, so here dash line defines the control volume boundary, and the energy of the mass at inlet is given by this term. Okay, energy of the mass leaving is given by these three terms, which we have just studied. So now if we apply this E dot in is equal to E dot out, and then we can transform that equation, this general equation, in this form. Right. So here are the energies entering and energy leaving. So Q minus W is taken because Q is entering, W is leaving. So that's why it is Q dot minus W dot. So it is the same equation. So there is no W in, there is only W out. So that's why Q in minus W. Q minus W is shown here. Because Q is entering, W is leaving. This is the mass which is leaving, and this was the mass which was entering. This was here, and it is taken here. So that is the general equation for this exemplary system. Right? So here now we can write it in this form, because the total amount of mass flow which is entering will be equal to the total amount of mass flow which is leaving for a steady flow system. So this m dot at outlet is equal to m dot at inlet. So we can write this form in this equation in this form. So here you have written H2 or H out minus Hi, or it is written as H2 minus H1. Similarly, velocity change from inlet to outlet is given by V2 square minus Vi square, or V2 square minus V1 square by 2. Similarly, the change in potential energy, final minus initial, G into Z2, because G is constant acceleration due to gravity. Right, so that is the energy balance of this system, and we can write it for a unit mass basis. So everything will be smaller units. All the extensive properties will be represented in terms of in the form of smaller symbols. Right. So that is the energy balance, the same energy balance for a unit mass. Right. So when this fluid, when it is flowing through this control volume, it if the changes in kinetic and potential energies from inlet till exit are negligible, then this equation reduces to this simple form: Q minus W is equal to H2 minus H1. So depending upon application to application, in some applications this velocity change would be negligible, this V2 minus V1. In some cases this Z2 minus Z1 is negligible. So in most of the cases, we shall see in most of the thermodynamic system, this is not negligible. So in most of the thermodynamic systems, this change in enthalpy, we will see that this is not a negligible quantity. But kinetic and potential energy changes are could be negligible in various thermodynamic steady flow devices, which we will now discuss again in the coming slide. So we're just for a review that this Q is actually Q dot divided by M dot, and this W is small w is actually the capital W divided by M dot. So we have divided this work or total amount of Q with the mass. That's why it is small q or small w. So this is the equation. In this equation, Q is clear. Q is representing the amount of heat, and we already know what is meant by heat transfer, right? So that is the energy which is crossing the system boundary due to temperature difference. And what is W? So that is important. So here in this case, for a steady flow system, this W represents a work done, but it is not a boundary work, right? So that is important thing. So here, when we say this is the work which is crossing the system boundary in a steady flow system, so this work is not the boundary work, because for a steady flow system, this is a steady flow system, and this is its boundary. So the properties, the thermodynamic properties, change at the boundaries. No, they do not change at the boundaries. Thermodynamic properties, they do not change at the boundaries with respect to time. That is the characteristic of a steady flow system. So therefore, the fluid properties at an inlet or exit will remain the same during the whole process. They can be different at different openings or different outlets, but at one particular outlet or at one particular opening, these thermodynamic properties do not change with respect to time. So here what we are saying that no properties change at the boundaries with respect to time. This means that the boundary work cannot be done, because if this work is a boundary work, so what is boundary work? Where the boundary moves, right? So what we have learned in chapter 4, boundary work means whenever there is a work done and the boundary itself is moving. So when the boundary itself is moving, this means boundary work cannot be done as work, because this work would change the fluid properties at the boundaries. When this work is moving boundary work, so moving boundary work simply means the properties, thermodynamic properties like pressure and volume, or speed or velocity or temperature, they would be changing at the system boundaries. So that's why this work is not boundary work if it is a steady flow system. So then what kind of work is this one? Because there is not only one form of work, and that is boundary work. There are other forms of works also which may be crossing the system boundary. So what are those? So work required. So there is a work required to push the mass into the system. That work, which is the PV product, that has been accounted here by enthalpy, because enthalpy incorporates this work, which is the pushing work, and also this work when the fluid is leaving. So that PV work is actually included here. So this PV work, which is required at the inlet and at the exit, is not this one, right? And this one is not a boundary work, right? So then what kind of work it could be? So the W dot then represents the remaining forms of work. If it is not a boundary work, if it is not a pushing work for the mass to go into the system or leave the system, then what type of work is it? So this represents the work like this one. This could be a shaft work. Some shaft is crossing the system boundary and work is transferred to this fluid, to this control volume. Or it could be an electrical work. Electrical energy is entering, right, and it is transferring energy to this control volume, and then it is leaving. So this kind of this work in this steady flow system, either it could be a shaft work or it could be an electrical work. So it cannot be a boundary work. Boundary work simply means the boundary. At the boundary, the thermodynamic properties would be changing, and that violates the definition of steady flow. So we are discussing steady flow devices. So that W dot here in a steady flow system represents shaft power, if it is turbine, compressor, or pump. So in all these devices, turbines, compressors, and pumps, the energy which is supplied or which is taken out of these devices is in the form of shaft work, right? Or it could be electrical work, right? If control surface is crossed by electric wires. If nothing is present, no shaft work, no electrical work, no boundary work, then we can simply say this work done is zero. Then what is change in enthalpy? This delta H, that is clear enthalpy change of a fluid, which we can find out from tables or charts, We have already discussed how to use tables to find out these enthalpies, to calculate these enthalpies. For example, at this point, if temperature, pressure is given, we can find out its enthalpy, or temperature and volume is given, then we can find out enthalpy from steam tables. If the working fluid is steam or some other fluid, we can find this enthalpy with the help of other intensive thermodynamic properties. At least we need two independent intensive thermodynamic properties to calculate this enthalpy. So we know already how to calculate this enthalpy using tables, right? But for ideal gases, we can find out this change in enthalpy. If there is no table available, then we can use this equation, because we know this change in enthalpy is given by Cp dt. And we have already discussed in chapter 4. Cp we can find out from tables, from charts, or from by integrating an equation, because this Cp is a function of temperature, or we can use an average value over this temperature for this temperature change. So now let's discuss the change in velocity and change in potential energy. Change in kinetic energy is given by V2 square minus V1 square by 2. So in some cases, this change in kinetic energy could be negligible. Kinetic energy term, we will see that this change in velocity, this change in kinetic energy due to change in velocity could be negligible. For example, if V1 here is, for example, is a very small value, this V1 is equal to, for example, 0 meter per second at the inlet, right? And at exit, this V2 here, this VE or V2 is, for example, 45 meter per second. So that represents a very high change in velocity. It's magnitude wise, it's a very big change from 0 to 45 meter per second. So 45 meter per second, you can imagine if you convert it in kilometers per hour, it is about 1800 kilometers per hour. 1800 kilometers per hour. So if there is a velocity change from 0 to 45 meter per second, it represents a change of about 1800 kilometers per hour. So it's a huge change, but that is velocity change, not energy. What will be the energy change? So now you have to find out V2 square minus V1 square divided by 2. That will be the change in kinetic energy. So now if you just put here 45 square, right? 45 square minus 0 divided by 2. Then what will be the units? It will be meter square divided by second square, and that is equal to joules per kilogram, which we have already discussed a number of times in previous chapters. So if you want to write it in kilojoules per kilogram, then you have to divide this by 1000 also. So you have to divide it by 1000 also. So if you divide it by 1000, then it is kilojoules per kilogram, and when you will notice that this value comes out to be only 1 kilojoules per kilogram. So this change in kinetic energy due to change in velocity from 0 meter per second to 45 meter per second, this huge change in velocity, when you convert it in terms of energy in kilojoules per kilogram, it represents only 1. Right. So this value seems to be a very small value compared to the enthalpy change. So you would the numericals which we have solved in previous chapter and the numericals which we will solve in this chapter, we will see this change in enthalpy would be much larger than this value of 1 kilojoules per kilogram, right? So that's why in many cases you will see that this change in velocity or the change in kinetic energy from inlet to outlet compared to the changes in enthalpy, that change in internal energy is negligibly small, right? So that's why we use that assumption in several places, that the changes in kinetic and potential energies are negligible, which you can see here by solving this question, right? this example which we have solved. So this kinetic energy term at low velocities can be neglected. I have given this example. Right? This change in velocity of 45 meter per second represents a kinetic energy of only 1 kilojoules per kilogram. Right, so fluid stream enters and leaves a steady flow device at about the same velocity. If V1 is nearly equal to V2, then we can simply say this delta KE is 0, or the change in kinetic energy is 0 regardless of the velocity. So if V1 is 0, V2 is 45, the change in kinetic energy is only 1 kilojoules per kilogram. If the inlet velocity is 50 to 67, now you can see the change in velocity is a smaller value, but it also results in the same kilojoules per kilogram because the initial velocity is higher. So that's why here V2 is now 67 square minus 50 square. So that represents a change of 1 kilojoules per kilogram. So if the inlet velocity is increasing, then you need a very small change in velocity to which corresponds to 1 kilojoules per kilogram. Right, so that is the case. Like for example, if the inlet velocity is very high, is already 500 meter per second, and if there is a change of 2 meter per second only, then this change at such high inlet velocity represents a change of 1 kilojoules per kilogram. So that is the conclusion. At very high velocities, which you can see here, even this small change in velocities can cause a significant change in the kinetic energy of the fluid. So if the fluid velocity is already very high in this region, then the change in velocity could be a significant value. If it is changing from 500 to 600, then this value could be a very large value and it is not negligible. Right. Now we can discuss the potential energy change, because this energy change also we considered negligible in most of the thermodynamic systems like turbines, from the inlet to exit of turbine, or from the inlet to exit of compressor, or from the inlet to exit of pump. Why it is considered negligible? So here we can perform the same example for which we did in the previous case for velocities. For example, potential energy change. If we want to find out this potential energy change from this point, this is inlet and this is exit. If for example this change in height from inlet to outlet is 102 meters, 102 meters, it's not a small change in height, significant change, 100 meters change in height from inlet to outlet. If this change in height will result in the change in kinetic energy of only, again, 1 kilojoules per kilogram. So if you put here Z2 minus Z1 as 102 multiplied by 9.81 divided by 1000 to convert it into kilojoules per kilogram, so it again comes out to be 1 kilojoules per kilogram. So in most of the thermodynamic systems, like in most of the thermodynamic devices like steam turbines or pumps or compressor, this change in height from inlet till exit is normally less than 100 meters. So that's why only in the case of hydraulic turbines this change in height is significant. It could be in thousands. In that case, this change in kinetic energy is not negligible, but in other thermodynamic systems, like in the devices which are used in steam turbines or gas turbines, the change in kinetic energy from inlet to outlet is the change in potential energy from inlet to outlet is negligibly small because of this smaller change in height. Although it seems very large change, but when we convert it in kilojoules per kilogram, it comes out to be only 1. So again, this change in potential energy from inlet to outlet compared to change in enthalpy, that is again negligibly small. So that's why in most of the cases, this elevation difference between inlet and outlet in most industrial devices such as turbines and compressors is well below this 100 meters. So the change in potential energy will be less than 1 kilojoules per kilogram. So this term is significant in process which involves pumping of a fluid to a very high elevations. and pumping power is required to be calculated. So if this height change is significant, then maybe this potential energy change is not negligible.